Property 4 in ring homomorphism. Let pi be a ring homomorphism from a ring R to a ring S, and B is an ideal of S, and we have to prove this set is an ideal of R. Given the pi is a ring homomorphism from a ring R to a ring S, and they give B is an ideal of S. Here the given set, we are considering the whole thing as A equals to given set. Since before going to prove it is an ideal, we have to prove it is a non-empty set. For that sake only, we have the property already. Pi of 0 equals to 0 dash means 0 exists in this set. Means if pi of 0 instead of R, if belongs to B, then it will be belongs to pi inverse of B. In the same way, if pi of 0 equals to 0 dash, already we have from property. That's why we are writing the 0 belongs to pi inverse of B. Pi inverse of B is nothing but A, means 0 belongs to A. We can say A is a non-empty subset, and it is also subset to R because the 0 exists in R also. Now we have to prove pi inverse is an ideal if it satisfies the conditions. The conditions of ideal are, the first condition is A minus B belongs to pi inverse of B. We have to prove this first condition. The second condition is right ideal AR, left ideal RA belongs to pi inverse of B. If these two satisfies, then we can say the given set is an ideal. Now proving the first case, for this one we are taking some elements A, B belongs to A, where pi of A, pi of B are the elements of B. Now consider here we are considering pi of A minus pi of B. You just see the given set elements like this. Means the elements in B are in terms of pi of R. If it is A, B, we will write it as pi of A, pi of B like that. That's why we are taking pi of B are the elements of B. Now considering the elements pi of A minus pi of B equals to B. By using the homomorphism, we can return this one as pi of A minus B, which belongs to B. Now the element belongs to the B means, you see in the given set, the element belongs to the B means that will be equals to the pi inverse of B. Means we can write A minus B belongs to pi inverse of B. That implies A. The first condition is satisfies. Next condition we have to prove left ideal and right ideal. Now in the statement they gave B is an ideal of S. B is an ideal of S means the B elements are in the form of pi of A, which belongs to B, and the S means instead of R we will take S here. Pi of R belongs to S. Now left ideal means instead of A, R, we will take here pi of A into pi of R, because here B is an ideal of S. So taking the conditions of B is an ideal of S, we have to prove the set is an ideal. For that sake we are taking pi of A into pi of R, left ideal, right ideal, and pi of R into pi of A are present in B. This is right ideal, this is left ideal. Now pi of A into pi of R belongs to B, and pi of R into pi of A belongs to B, and the elements in the pi of A, pi of R belongs to B, we can return as, using the multiplication homomorphism, pi of AR belongs to B. This is also we can return as pi of RA belongs to B. Now pi of AR belongs to B means how we are writing AR, RA means, you just see in the first, to prove it is a non-empty set, we have the property pi of 0 equals to 0 dash. Now we are writing directly 0 belongs to A. A means how we are writing the element which is there in the bracket of pi of 0, that is belongs to the A. In the same way, here pi of AR belongs to B means the element AR will be belongs to A. In the same way, this RA also belongs to A. Means this is a right ideal, this is a left ideal. So we can say from equation 1 and 2 satisfying the conditions of ideal, so we can say pi inverse of B is an, hence we can say pi inverse of B is an ideal of R. Next property 5, let pi be a ring homomorphism from ring R to a ring S. We have to prove two conditions. One is if R is commutative, we have to prove pi of R is commutative. Next one, R has a unity element 1 and pi is onto, then we have to prove pi of 1 is a unity of S. Given proof, they gave R and S be two rings and pi mapping from R to S. Here R is a commutative ring Let the homomorphic image of R be pi of R. Here we have to prove pi of R is commutative. Now we are taking an element x comma y belongs to pi of R. Now x comma y belongs to pi of R. We are considering the pi of A value as x, the pi of B value as y. To prove it is a commutative, the condition of commutative is AB equals to BA. Instead of AB, BA, here we are taking XY. We have to prove XY equals to YX. Now considering the LHS part, XY equals to, what is X value is pi of A and Y value is pi of B. In the next case, given ring is homomorphism, we can return as by using the multiplication homomorphism pi of AB. Since R is commutative, since R is a ring, it satisfies the associative. So AB can return as, since R is a commutative, we can return as AB as BA. And the next step, we can write this BA using the multiplication homomorphism pi of B into pi of A. Means pi of B value is nothing but y, pi of A value is x. Now you see xy equals to yx, means pi of R is commutative when R is commutative. Let pi mapping from R to S is a ring homomorphism. Now we have to prove second condition, pi of 1 is an unity of S. Now unity element we are taking as pi of 1 belongs to S. Now unity element is nothing but we have to prove the condition of identity. Identity property is A dot 1 equals to 1 dot A equals to A. This is the identity property. Now what is the identity here? Pi of 1 is identity. Now take an element A belongs to R and A dash belongs to S. If it is A dash and that A dash will be belongs to pi of A, since pi is on onto, it have an image A dash equals to pi of A. Now we have to prove an identity, means two conditions. Here identity is pi of 1 and element instead of A is A dash equals to, we have to prove equals to A dash. This is the identity we have to prove. Pi of 1 into A dash into pi of 1 equals to A dash. This is the identity. Now we are taking this part pi of 1 into A dash. Now pi of 1, A dash value is nothing but pi of A. By using the homomorphism we can return as pi of 1 into A. Pi of 1 into A can return as A and pi of A value is A dash. Pi of 1 into A dash equals to A dash. Now first condition is satisfied. Next one you have to take this one. A dash into pi of 1 equals to, what is the A dash value is pi of A into pi of 1. By using the homomorphism we can return as combinedly A into 1. This is nothing but pi of A and pi of A value is nothing but A dash. Both the cases you got A dash, so we can write combinedly pi of 1 into A dash equals to A dash into pi of 1 equals to A dash. This is nothing but the identity property. Here identity is pi of 1. Pi of 1 is a unity element. Hence pi of 1 is a unity element of S.